right, we are live. Looks like we got about 16 attendees so far. We'll take the next few minutes to let everyone else join. If anyone has questions that they know they want to get down, feel free to put it in the Q&A and we can try to get to them at the end of the webinar here. All right, we are at the top of the hour here. We will get started. Hello, everyone. Thank you for joining us today to our AutoPipe webinar, Critical Piping Lifecycle Insight with Fatigue Analysis in AutoPipe Advanced. Why are we here today? Well, we just added fatigue analysis to our most recent update of AutoPipe that just came out at the beginning of this month. If you are already AutoPipe users, that would have gone in to your current license. If you are new to AutoPipe, haven't used the program before, today we will go through the workflow and show you a little bit what this program can do. Fatigue analysis, special type of damage that we see in these piping systems that can really restrict the life of the plant. With fatigue, we're looking at loads that are applied and taken off that are within the scope of the project, but that repeated loading can cause lots of damage, eventually critical failure. We're going to talk about this today with our Bentley pipe stress expert, Joshua Taylor. Joshua is one of my colleagues here. He's a senior software engineer with our AutoPipe team. He's been here for 13 years, and he's an expert in linear, nonlinear, and dynamic structural analyses, as well as many common code compliance design criteria. He works in nearly every aspect of AutoPipe. He loves critical thinking, problem solving, infrastructure, and looking at these easy-to-use features such as this fatigue analysis we're going to be digging into today. Joshua is going to go through a few slides. We'll look at what is fatigue analysis in general, how is it applied to AutoPipe, and then he's going to walk you through a fatigue analysis problem, going through the workflow within AutoPipe Advanced and showing you how easy to use this feature is and how effective it can be when looking at project lifespans. Joshua, I will turn it over to you.
All right, thank you, Shyla. And thank you to those who are attending today and interested in learning about this exciting new feature in AutoPipe Advanced. Today, as Shyla was saying, we will be covering the topic of material fatigue, how it can affect your plant, and how we can use AutoPipe to evaluate models' design lifetime. We leverage AutoPipe's highly refined, detailed, and battle-tested stress analysis results to determine exactly how many cycles your plant can withstand. The tool we will explore together is customizable, it's extendable, and it's precise. So first off, let's begin by asking the question, what is fatigue and why do we care so much about it? Well, material fatigue specifically is an evaluation of progressive cyclical structural damage. Pipes are unfortunately not isotropic, as tiny defects that we call voids are introduced into the lattice structure of the material of the pipe during the formation process. As stresses are loaded and unloaded over time, these microscopic voids will enlarge, they coalesce with neighboring voids, and these voids eventually reach a critical size that, while still being microscopic, can cause the whole material to fail suddenly. Failure is not specific to any one load type, be it operating condition changes like temperature and pressure, or mechanical loadings like earthquakes, harmonic loadings, and so on. Every industry can be affected by fatigue, but the most impacted are the oil and gas, chemical, refining, power industries, with fatigue accounting for roughly 80% of industrial failures. Parts subjected to these types of cyclic loads are likely to fail even when the loading is much less than the documented yield strength of the material. A carbon steel pipe with a yield of 35,000 psi can still fail when the peak fatigue stress range is even 20,000 psi. Stress fractures can happen suddenly, even when the pipe in operation continues to appear elastic. When it comes to safety and cost, the primary threat to the integrity of piping components is fatigue and fracture, which can result in serious injury, loss of life, near or widespread environmental damage, and economic loss. Evaluating fatigue damage is similar to how we calculate stress damage in AutoPipe, where the number of expected cycles divided by the allowed number of cycles based on your peak fatigue stress provides us a damage ratio that we call a usage factor. Determining this factor in autopipe is a two-step process. First, by selecting a fatigue curve on your pipe, and then second, by applying a load transient profile on your model. So let's look at the first phase. Experiments have been devised where specimens of various material types are subjected to cyclic load until they fail. These empirical results are plotted into what is known as a fatigue or an SN curve. The name SN curve is derived from the axes of the curve, where S is the peak cyclic stress of a load transient being a plant going from one state to another. And N is the allowed number of cycles for that material before failure occurs. Typically, these are plotted on a log-log scale, and they look like this. Here we have one of 9 curves that Autopipe supports from ASME BPVC Section 8, Division 2. This curve, for example, is for a carbon steel pipe composition with a maximum ultimate tensile strength of 80 KSI. We provide an additional 10th curve, which is derived from ASME B31.3, Appendix W. Autopipe's built-in curves are numerically evaluated rather than being a table lookup to provide you high precision results in the higher end cycle allowed. We support a unique curve for every pipe property that you define in your model, and a custom fatigue curve can be created by you at any time to represent any curve that you wish to use. We will look at custom fatigue curves in a little bit. But for now, we will move on to the second phase of the fatigue design, which is loading. Fatigue loading in Autopipe, or loading in general in Autopipe, is a little bit more complex, as we support a myriad of different types of loads that your model may be subjected to during its lifetime, from pressure, temperature, and dead weight, to wind, static seismic, fully reversing dynamic loads such as harmonics and response spectra, time history, and seismic anchor movements. All of these loads and more that are available in Autopipe will be at your disposal when creating a fatigue loading profile. Fatigue load transients are typically framed by 2 operational states known as load sets. For example, a 2 load set transient might range from a cold condition to a hot operating condition for your plant or component. In Autopipe, we define these operational states in this way. First, load cases like temperature and pressure are defined during the design process. Analysis sets are created to apply these loads onto the model to obtain stress results that we require, the results of which are combined in our post-processor with other load case results to create a load combination state, which can then be used as part of a load transient. So a load combination like the one that I have highlighted here, GRP1T1, means that all 3 loads are occurring at that state, so that would be a conditional state that your plant is operating at. Note that we use general principle stress results to determine the peak fatigue stress, which is done so that no specific piping code is required to use our fatigue module. So it's a general fatigue, it uses general stresses, so you don't have to specify a particular piping code. After defining the 2 states of a load transient, you must also specify how many cycles will occur during the lifetime of the plant. This will be compared to the allowed cycles from the selected fatigue curve to produce a usage factor. A usage factor above 1 would represent a part failure prior to the end of life of that part. And from here, if you are exceeding a value of 1, designers can then redesign the model geometry, reduce loading, or reduce the number of cycles to keep this factor below 1. It's important to note that a passing fatigue report in your model does not imply that it will pass code compliance, so do be sure to check that report as well. So now that we've done that, let's take a look. Now that we've gone through a few slides, we're going to take a look at a real model example and see what kind of data we can obtain. I'm going to look at the other monitor over here. We have a model in AutoPipe that's under review. I've colorized this to make it a little bit easier to see the different pipe properties that exist in this model. We have 3. And today we're going to be looking at this T-junction that's occurring. So we have some material flowing into the system here and coming down into a turbine that's down here. And we have this branch of austenitic steel that is coming off of the side. We want to look at this T-junction for fatigue. So the first thing I'm going to do is I'm going to show you the first step of the process, which is to define a fatigue curve. If I open up this 6-inch standard schedule pipe, this yellow color here, and click OK, we can see that a form opens that provides information about the pipe itself, including the geometry of the pipe, the material of the pipe. So you can see here I'm using an SA 333-6. We have the cold allowable, the minimum yield, the ultimate, and then down here, the ultimate tensile strength, and then down here we have the fatigue curve. So this field and the environmental factor are 2 new fields in this form. If I click this drop down here, you can see that we have a number of different fatigue curves that we provide, including the 9 curves that I was telling you about. These are curves that are calculated using equations. Up here at the top, we have ASME B313 Appendix W. Down here, we have none. If you select none here, you're basically telling AutoPipe that you do not want to consider fatigue for this pipe property. For this example, I'm going to use an 80 KSI carbon steel because the material that we're using is a carbon composition and it has an ultimate strength less than 80 KSI. You can also create your own fatigue curves. I have an example here of what a custom fatigue curve might look like. This is one that we actually provide as well. It's found in the program directory of AutoPipe. It's a basic text file. It has an extension of .fat for fatigue. The values here for cycles are in ascending order, and the stresses here are in descending order. I would recommend, if you want to create your own fatigue curve, to go into your program directory and copy an FAT file out and use the same format. But if you create your fatigue curve and you put it into your model directory, you will see it pop up here in the dropdown, and you'll be able to select it there. The environmental factor is just a simple factor. It's a value of 1 or greater, and it is used to reduce the number of allowed cycles. So for example, if you have a stress range that's producing that allows for 100,000 cycles, if you put in an environmental factor of 2, it will reduce that down to 50,000 cycles. I also have, if I go here to the input grid, we can see, I'll pull this over here. We can see that I have some loading applied to this model as well. We have a few load cases here. We have some temperatures. So this is running at 650 degrees Fahrenheit at about 2200 PSI. We also have another temperature case here at 700 degrees, and a third case here that's kind of in the middle, about 665. I've also included in this model a static earthquake, a very simple static earthquake. It just has a 1g acceleration in the x direction. And after you define all the information in your model, you can go ahead and analyze that. So I'll just analyze everything that I have here. And what that will do is it will figure out the stiffnesses in the model geometry, including all of the supports that we have, the anchors that we have in here, and it will apply the loads and provide us some displacements and some forces and moments. And from there, we can calculate our stresses. Now that that's been analyzed, I'm going to go over to the results tab and click on our combinations button. Existing users of AutoPipe will probably be very familiar with this dialog. It contains information like the load cases that have been analyzed in the model, code combinations that were recommended, non-code or general combinations, general stress combinations. And there's this new tab here called fatigue. Fatigue has a grid here of information of inputs for the user. And if we just go through these columns, we can see that we have the index, which is just basically a number that's counting up. That's for your reference, as the output report will reference this index from time to time. The actual cycles so each of these rows would represent a transient, some kind of load transient that would occur. The actual cycles represents the number of cycles that you expect that transient to occur over the lifetime of the plant. We have these two load combinations. These would basically be your states or your load sets that for that transient, you're going from one state to another. So in the first case, for example, we're going from gravity, which is just the dead weight of the plant. There's no, you're at ambient temperature and pressure, up to this operating state, which is gravity, temperature, and pressure combined. So we're going from gravity to some sort of operating state. The order of these combinations does not matter. So here, for example, I'm going from gravity to GT1P1, and here I'm actually going from GT2P2 to gravity. So this would be the second operating case that we have here, 700 degrees Fahrenheit and about 3,100 PSI, internal pressure. So the order of these does not really matter. And then we have a description column here that is just for your information, anything that you want to put in here that describes the actual transient that you're trying to evaluate. We have 500 cycles here. We've got 45 cycles here. This represents maybe a minor power fluctuation or maybe a pressure fluctuation that occurs from time to time in your plant, and that's rated for about 5,000 cycles. And here we have two very special transients. These are what are known as fully reversing dynamic load cases, or a transient. And you can tell that this is a fully reversing dynamic load case because when you try to select a second combination here for this one and tab out, it will tell you that reversing dynamic load combinations cannot be ranged since they typically happen on short order, and they are going fully between complete compression to complete tension. We will only allow you to specify, so basically it's ranging itself. I want to specify also that if you're using one of our fatigue curves like ASME Section 8 or ASME B31.3, one of the equation curves that does not have an FAT file attached to it, those typically will use hot material properties in the equations themselves. So if you're using a reversing dynamic load, like say, for example, if I'm looking at this harmonic case autopipe, and the same with static seismic, autopipe is going to assume that this is running at ambient temperature. So you'll effectively be using cold modulus and cold yield to determine the number of cycles that are allowed for that load set. So what I want to do is I want to include temperature. Let's say that I want to have this harmonic case, if it's a turbine, say, and I want it to be running at an operating state. What I need to do is I need to specify a temperature to go along with this. And since all of these combinations here are coming from our non-code combinations tab, this is our general combinations. So if I go over here, and you can see that there's some information here about all the different combinations that were created as a result of the analysis. These ones that are highlighted in magenta are already being used in our fatigue. But if I want to create a harmonic case that is at, say, our T1 that is using our first temperature case, I can create a new combination and use that in our fatigue as well. So that's part of the customizable part of the fatigue feature. So we can name this whatever we want. Let's say I name it H1 at T1, set the combination method to sum. For the first case here, I'm going to use H1, which is our harmonic case. And I'll specify our T1 here for the actual hot modulus case. Now, what you're telling autopipe at this point is that you want to consider the stresses that are being caused from temperature being loaded and unloaded. We don't want that. We just want the temperature. So I'm going to set this moment factor here to 0. And that way, it's going to only consider the moments, the loading due to the harmonic load itself, but it will use this T1 temperature, whatever that temperature is, for your hot modulus. And again, this is used to evaluate how many allowed cycles you have. The higher the temperature it is, the less allowed cycles you'll be that you will have. So it's important to consider that as well. So we'll click OK to create this combination. And you can see it pops up down here at the bottom. But I haven't specified this with fatigue yet, so I'll go back over to the fatigue tab. And let's say that I want to change this harmonic case. Or you know what I'll do is I'll create a new transient here by clicking New. And let's say that I specify that again for 5 million cycles. Come down here, and at the bottom of this list, you can see that our new combination is there ready to be used. You can then delete this harmonic case if you wish, if you don't need this, this transient anymore, or if you want to just ignore, if you want to keep that transient, but you don't want it to be shown in your fatigue, you can set the allowed number of cycles to 0. And what that will tell AutoPipe is when you generate the fatigue report, I don't want to see this load transient in that report, and it will not contribute to the usage factor. All right, so we'll click OK here. And let's generate an output report and see what we get. So again, we're going to be focusing on, and let me actually just quickly make sure I have selected that point. We'll go here, and we want to look at this particular T point, like I said at the beginning. I'm going to print out the analysis summary, which gives you just a general overview of the analysis and how your post-processor, your code compliance combinations, and your general combinations and your fatigue is configured. I'm also going to print this fatigue report that will show the actual results of our model. I will bring this over here. So here you can see the top of the report. If we come down here, I've also printed the pipe data listing report, which gives you an echo effectively of the pipe data, the pipe properties data in your model. So it contains a lot of information from that form. You will also see that we have the fatigue curves here on each of these pipe properties. And as I said at the beginning, you can have a different fatigue curve for every pipe property in your model. So the branch here was already pre-configured to use an austenitic steel curve because it is an austenitic stainless steel pipe. The one that we're looking at is the 80 KSI carbon steel because it is a carbon steel pipe. And you can see that we've also added the environmental factor as well. We've left that to 1 for right now, so you can see that that's being printed at the bottom of this table here. If I scroll down to the analysis summary, this is sometimes a few pages, but this covers all the information about the different analyses that were run. If I continue to scroll down here past all of the different dynamic analysis that's been performed, the harmonic case that we're going to be looking at, you can see the table of the code compliance configuration information. We'll skip past that. We can see our non-code combinations. That was the general combinations that we were looking at before. And you can see at the bottom of this table, of the non-code combinations table that we have here, our H1T1. It includes information like our harmonic case, our temperature case, and you can see that that factor has been set to 0. Again, that means that we want to use the temperature for that case to calculate the hot modulus and thereby calculate our allowed cycles, but we do not want to consider the stresses that are caused from going from ambient to T1. And right after the non-code combinations here, we can see the fatigue table, which again is kind of a configuration echo of the information that we put in. So we have the descriptions, we have the indices, the allowed cycles, and all of the combinations as well. If I continue on down past all this information here, we can get down to our fatigue report. Our fatigue report is printed per page per point in the model. Again, I'm only looking at this T, so we're only seeing the information for that T. If you were to print all the points in the model, you would have a page for each point in the model. And each of these reports are split into two different tables. We have the load sets table and the load set pairs table. If I open up the combinations really quick here, just so we can see a side-by-side comparison, I'll bring back the report. So the first table, what we do is we actually take each state from each transient and we break them into their individual load sets. The second column here is the index that reflects the index from this grid. So you can see that this first load set was the first state from the first index, whereas the second load set is the second state from the first index, and so on down. We have the actual cycles, the load combinations, and then some basic general information about each of these combinations at their state. So for example, gravity is producing no hoop stress. That makes sense because there's no pressure, there's no internal gauge pressure to consider here. It also has the shear stress, the longitudinal max and min, your principal max and min stresses, and then your total peak fatigue stress, which is the combined stress of the principal stresses. So this has all the information about the different load sets. Now we'll talk about how AutoPipe actually calculates the load set pairs. Typically, what we do is, in order to produce the most conservative number of allowed cycles, we will range each load set, each static load set. So for example, these first 6, the ones that are not reversing dynamic, which would be these ones here, we will range each load set with every other load set to figure out which one produces the maximum peak stress. So for example, this first load set pair is load sets 1 and 3. It has the maximum peak stress of 19,000 psi, which is just the difference of these two stresses, of this stress and this stress, divided by 2. We divide it by 2 because we split the actual cycles here and here. So we'll take the actual cycles that you provide and split it here and here and have the stress. The used cycles for this would basically be the lesser of the two of pairs 1 and 3, whichever one has the least amount of cycles remaining in it. So in this case, we have 45, and that's because load sets 1 and 3 has 500 cycles and 45 cycles. The lesser of that is 45, so we place that here. And then we have some information about what remains after those cycles have burned down, so to speak. So in all of these cases, you will have a 0 in one of these two columns. So here we have 0 because 45 is how many was used, and it only had 45 to begin with. The first load set pair has 455 because that's 500 cycles minus 45 cycles spent. So there's 455 remaining. The allowed cycles is will be coming from your SN curve that you selected in the pipe properties dialog, and that's derived from the peak stress. So if you were to take this peak stress and look at it on the fatigue curve, you would get approximately, or you would get 109,532 cycles allowed for that load set. So what that basically means is that that load set pair could potentially happen 109,000 times before this T point fails. That produces this usage factor. And we've also provided a cumulative column here to provide you a total amount of usage factor or fatigue damage that might occur on the plant. Continuing down, just one more. I know we're kind of short on time, but we'll skip this. But basically, you can see that the 455 cycles that are used here again is the lesser of the two, 1 and 6. Analysis set 6 has 5,000, and load set 6 has 5,000. Load set 1 has 455 because that's how much remains on that load set. So we're down to 455, and now you can see that that's been completely burned down to 0. If you see something like this, 7-0, that means that it is a fully reversing, or basically it works on itself. So 7 was your static seismic here. It has 11,477 PSI. It uses up all of its cycles, and it's allowed that many cycles, so it produces a very small usage factor. And you can tell from this model that we can already tell from here that we've already failed because it's going to exceed the usage factor before the end of life of plant. The last thing I want to mention here is this note 2, which you might see from time to time. Autopipe supports an allowed cycle limit of 2 billion cycles. If the peak stress is low enough that it produces more than 2 billion allowed cycles, we basically say that it's effectively beyond the endurance limit. So this note 2 here is referencing this note at the bottom of every fatigue report that states that the fatigue endurance limit has been reached for this and all following load set pairs. In the load set pair table, peak stress is sorted in descending order, I mean to say, which means that this peak stress is too low to produce any significant fatigue damage to your plant. And so the rest of these will not print any allowed cycles, because anything after this, you will not see any damage. And I think that's my time. So now we will move on to questions. All right, I have a question here asking for user-defined fatigue curves, how many data points can be included? So for these FAT files, that you can create any FAT file that you wish for any material that you wish, and it will still be applicable within Autopipe. You are allowed up to 100 different data pairs. Remember that this is a log table, so consider that as well, but you're allowed up to 100 different data pairs. Okay, I have another question here. How many load transients can be created? So if I go over here. So here we have in this example, it was very simple. We were just using 6 load transients. Autopipe can support up to 1,000 different load transients. They all have to be unique. You can use the same load combinations in different ones. Like here, I don't think I have an example. Oh, I do, yeah. So here we have GT1P1, and here we have GT1P1. But if you can't, I would not be able to select, say, Gravity 2 here. It would, because it's a duplicate of the same one, so it won't allow you to do that. But you're allowed up to 1,000 different fatigue pairs, fatigue load transients, I mean to say. I have a question on a heat map for the cumulative usage factor. We do not support that at this time, but we do have an ideas page on Bentley, and we welcome your ideas, anything that we can use to expand on this. You can do, so of course, at the end of each fatigue report, you have your total cumulative usage factor here. You can also export through Excel reports the fatigue report itself. So if I go here, and let's see, somewhere here, so we have the fatigue load set table and the fatigue load pairs table, and that contains certain information. I'm not going to go into details about how to set that up, but you can move these over and generate an Excel report, and you can sort by cumulative usage factor to see where the maximum is. But as for a heat map, I do invite an idea. Are there any code requirements to run fatigue? Nope. So we're basing this off of the general stress report. So if well, I won't open it up, but yeah, we use the general stress report. We use the principal stresses. And the reason that we did that is because we want to ensure that anybody using any code, I think there are some restrictions, but I think it's KHK2, for example, we don't do fatigue on, but any other code, be it EN 13480, B314, B314 offshore, CSA, you should be able to use fatigue analysis for that. Let's see. Okay, so how do we get so let's see here, for load set pair 1 to 3, how do we get the peak stress, the total stress of 3? Yes, so if I go back to this, so We actually take, so we will take this value, and so let me actually open up, I can open up a calculator here. So because we're effectively doubling the actual cycles. When you enter in 500 cycles, we're doubling it. We're putting it here and here. And to mitigate that, we reduce the total stress by half. So if we take, say, 40561 minus 2547, that gives us that stress. If I divide that by 2, it gives us the 19007 that's here. Let's see. Reverse dynamic loads and how you set it up. How can you please explain further on reverse dynamic loads and how you can set it up to be reversing an autopipe? So reversing dynamic loads are, so in autopipe, if I open up here the dynamic analysis, we have a number of different dynamic analyses that are available to you: response spectrum, harmonic, time history, and force spectrum. They're all based on modal analysis. They produce unsigned results because they move both in compression and tension. And you do not need to actually set up anything specific. So if I go to combinations and back over to fatigue, like I said before, if you can tell that it's reversing dynamic in 2 ways. One, because if I were to select a different combination here in the second load combination, it will tell you that it's a reversing dynamic load that cannot be ranged. Whereas if you're using, for example, gravity or temperature and pressure, those are different static states that you can range between. The second way that you can tell is in the output report. Under the load set pairs, we have a 7 and then we have a -0. That means that there is no load set for it to range off of. It's ranging off of itself. Because of that, we are using, so for example, this one here is a static seismic. It has 150 actual cycles, and we use 150 actual cycles. If you recall what I was saying before, we double the cycles when we have to split the static load sets apart. And so we have the total stress. But here, because we're not doubling the actual cycles, the total stress that's shown here is brought down and copied right here. So for both the static seismic and the H1T1 that we created, both of which are reversing dynamic, because they contain a reversing dynamic load, you can see that it is just copied straight down. Yep, so there's that. SN curve. The SN curves can also be found and used from ASME section 2. Is that correct? Yes. I mean, you can, if you, I'm not familiar with the ASME section 2 curves, but if you have a curve that you want to use, you can just put that into, you'd have to do it in a tabular format. But again, it would be a log. One question here is: the fatigue tab combination 1 and combination 2 are the same as the stress summary combinations? Yes. It works in a similar way. Please explain the 2 billion cycles. So 2 billion cycles is just a limit that we have. From what I understand, normally anything above 1 million cycles is considered the endurance limit, which means that it's not going to exceed the it won't cause enough damage to fatigue. It may vary from industry to industry. We have limited it to 2 billion. It's a relatively arbitrary number, but we feel confident that anything experiencing 2 billion cycles, that's a lot of cycles. And so we've used that limit. Yeah, and the one question here is: the cumulative usage factor the sum of all usage factors or the highest usage factor? Yes, it is the sum. So if you need just sort of a quick overview of a specific point, you want to see if you're failing or not, you would just look in the load set pair table and go to the bottom of the load set pair table, and this carries through. So if you were to take these numbers and add them together, so you can see that there's some cumulative factor that's counting up here, and then and it carries on down all the way through. So yes, it's a cumulative factor, not just the maximum experience so far. So you can see that the maximum here is a little less than the total cumulative factor. I think I'm not seeing anything else. It's kind of the Q&A is kind of jumping around, but I think that's pretty much all I have for today. Shyla? Shyla, back to you.
Testing.
There you are.
Oh, you can hear me now?
There you are. Hi.
Oh, great. All right.
I'm not even sure if I was muted. So I just, in case I was muted when I said what I said before, if anybody has any other questions, feel free to reach out. I'd be happy to help.
Let's see. All right. Can you hear me now?
Yes.
All right. Thank you. Okay. Sorry about that, everyone. Not sure exactly. And now I have some sort of weird echo going on.
I hear no echo.
automatically included in your license. Let's see any other questions I see here. I apologize for the technical difficulties I'm having here. If everyone was able to hear that last bit I said. This fatigue analysis is available in AutoPipe Advanced. This recording is going to be available for everyone who was registered. It should be directed right back to the email that you would have used to sign up. You can also use the same link to access the live recording as well. Let's see any other last questions we see here. We do have some help available on our community pages. And as Joshua mentioned earlier, that is a page that we use to go back and forth. So you as users are welcome to put in your questions, comments, suggestions you have for the program. We can respond directly to that with you. I am pushing out some poll questions. Those should be popping up to you. If you are able to answer, those would be helpful just for our own records to kind of see what the all right. Let's see any other questions that have been coming up here. All right. I'm going to just keep on pushing the poll questions for the last few minutes here. Joshua, if there were any other questions you wanted to address, feel free to take the last couple minutes.
Let's see. What is the difference between? Okay, so what version of AP does this appear? This appears in AutoPipe 2025, as Shyla just said. This is available in AutoPipe 2025.0, and it's available for our advanced license. It is not available for the standard license at this time. And let's see, I thought I just saw another one here. How to load set pairs determined. Okay, so there was a question here about the fatigue report, how are load set pairs 1 through 3, 1 through 6 determined. So at this time, so when it comes to the load set pairs, we're producing the most conservative results that we can. So we actually will, we range each of the stresses together to produce the highest peak stresses, which produces the most conservative amount of cycles allowed. If you are looking for something more like a strict fatigue transient, please provide that. And if you hop on our ideas page on the Bentley website and provide us an idea, we'd love to hear from it. I could definitely envision having a strict transient where we specifically do just exactly these. But for this feature, we're looking to produce a conservative result for our users, and we can go from there. So this is kind of a nice baseline feature for us.
All right, and we have our last poll question going out. And once you've answered that, we are done for the day. Please feel free to pop in any additional questions you have. We will continue to answer them. We can respond directly to you, especially if you put your email or ask for something else directly. We will also, especially if you responded to the poll question that you're interested in a demo, we will of course reach out and we can talk further about any direct questions that you have. If you'd like, feel free to reach out directly to myself or to Joshua to talk further about this license. Any technical questions, Joshua will be able to answer those. Anything regarding licensing or upgrading your current license, looking at your account, I can help you out further with that, and we will be able to get you set up with this really awesome analysis. Thank you, Joshua, so much for your presentation today. It was really helpful. And thank you to everyone who joined, everyone who asked questions. We really appreciate your participation in this and making sure that we're able to give you a webinar that's really focusing on the type of problems that help you most.
Thank you very much.
All right. Thank you, everyone. Have a good rest of your day.